Hi, hello, welcome to section 2 of chapter 6. Or in other words, welcome to my favorite concept in chemistry, the electronegativity. In this section, I'm going to talk about electronegativity and polarity and its applications of finding a dipole moment in a bond and what types of bonds out there and what is the ionic character and how to calculate all of these things we are going to do in this section. So let me repeat. If I have to choose one particular concept of all the concepts in chemistry to explain anything, I would go for electronegativity almost all the time because it is such an influential concept in our nature that exists between atoms that are making bonds. Um, Electronegativity for me is everything when it comes to chemistry. So without the help of electronegativity, I cannot explain many things in nature. It is so important. So we are going to learn about it today, and I hope you appreciate the electronegativity as much as I am, because this is my favorite concept again in chemistry. All right, let me define what is an electronegativity is. Electronegativity is the ability of an atom in a compound to draw electrons to itself. That's all electronegativity is. Again, it is ability of an atom to draw electrons itself. Okay. Why are we talking about drawing electrons itself? Is because if you guys remember in section 1 of this chapter, we talked about octet rule, which is having noble gas electron configuration by having 8 electrons in its vicinity. Okay, so atoms, having a driving force of having octet rule electronic configuration, they share electrons. Okay, but as we know so far, not all atoms are created equal. Some atoms have, well, all atoms have different number of protons and so different number of electrons. And those atoms come up with the different sizes. Some of them are larger, some of them are smaller. And it affects its atomic radius and how farther it is from the outside electron. So every atom is not equal, right? Because every atom is not equal and their nature is also not the same. So because of that, some elements have this unique ability of kind of stealing electrons from another atom in a bond. I really like that. I personally don't steal in real life, but I love it when atoms does it because that's where the chemistry discussion starts. That's where the chemical reactions happening. Unless one of these atoms making the first move of trying to steal the electrons from another atom, we don't have anything that we have in this world right now. We cannot make any chemical reactions unless these atoms making the move of trying to steal the electrons from another atom in a bond. Okay, that's why I'm so excited about this. Yeah, let's see. So first I want to, go to basics and try to, make a logical explanation until electronegativity, how we come to this point. So before I introduce you the actual trends in electronegativity, I want you to make a logical connection between atomic radius and electronegativity because it sticks with you if you make connection like this. You already learn, the table that I'm showing here is for the atomic radius, the trends in atomic radius. We already learned that atomic radius increases from right to left and increases from top to bottom. Okay, so let me see it again. So from neon to lithium, atomic radius is increasing. Okay, look opposite now. From lithium to neon, the atomic radius is decreasing. Okay, let's exclude neon now because it is a noble gas, so it's not really factor much. So let's cut short to from lithium to fluorine. What is happening to the atomic radius is they are going from larger of lithium, even though 3 protons, lithium is larger compared to beryllium. Compared to boron, even though number of protons are larger, number of electrons are larger, from lithium to fluorine, the atomic radius is decreasing from larger to smaller to smaller to smaller. Okay, so now we are talking about in lithium, for example, 3 protons in a lithium nucleus versus 3 electrons outside farther in distance, versus in fluorine 9 protons in nucleus with the tiny distance that separates from outside electrons to the proton. So what you see here is the lithium electrons are farther from lithium nucleus, but fluorine electrons are closer to the fluorine nucleus than any other atom in that group. So when atomic radius is smaller, the outside valence electrons of an atom are really closer to the nucleus. What do we know about the charges in nucleus and the electrons is the nucleus is positively charged because of the presence of the protons, and electrons are, we already know that they were negatively charged. So there is an electrostatic attraction between them, so they attract towards each other. Now, because the size of this fluorine is smaller, it has the greater ability to attract more electrons. So if there is an electron exposed to fluorine, fluorine will snatch it really quick because fluorine nucleus is really close to the outside electrons. So it is kind of able to strongly pull the outside electrons, even though they don't belong to fluorine, very easily. That's what electronegativity is, trying to get the outside electrons towards itself. Again, look at the definition. Electronegativity is the ability of an atom in a compound to draw electrons itself. So what we know is the smaller the atom is, more powerfully it can attract electrons because not much distance between nucleus to the valence electrons. That's why smaller radius containing atoms will have greater electron negativity. Again, look from right to left now. So as you see here, the size of the atom is increasing, which means the distance from nucleus to last shell, the valence electrons, is increasing. So when this distance is increasing, the nucleus cannot powerfully accept other electrons because there is not much, strong attraction anymore as you increase the distance. So that's why fluorine has huge or the highest electronegativity of all the elements in periodic table because it has smallest atomic radius. And from fluorine to astatine, if you see here, the atomic radius is increasing in the period, right, from top to bottom. What it means is the distance from nucleus to the last valence electron shell is increasing when you compare from fluorine to chlorine, chlorine to bromine, bromine to iodine, and iodine to astatine. Because the distance from nucleus, if you think of this one as a nucleus, think of this one as a nucleus, and my hand is the valence shell. For fluorine, it is really close to each other, so it can take more electrons because nucleus is still powerful. For chlorine, it is farther. For bromine, it is farther. For iodine, much larger. For astatine, much larger. What this nucleus can do to influence any additional electrons is much more smaller in astatine compared to fluorine. So that's why fluorine is most electronegative. It is because fluorine is really smaller in size, it has the lowest atomic radius, so its nucleus kind of commanding the valence electrons of the fluorine and taking the extra electrons. So there are two trends you can see in electronegativity. You can say that from left to right, electronegativity increases, and from top to bottom, electronegativity decreases. Okay, it's kind of work like opposite to the atomic radius. If you see, it is increasing from atomic radius is increasing from right to left, but electronegativity decreases from right to left. And from top to bottom, atomic radius is increasing, but electronegativity decreases because electronegativity is kind of opposite to atomic radius. Again, I'm going to revisit this topic multiple times. I'm going to show you the chart and talk about trends because this is important. But if you look in terms of atomic radius, it is so easy to predict why electronegativity is different in the different atoms. So that's one way to explain it. Now let me lighten up and make a joke of atoms that has electronegativity. What you're looking here is, let's say, an atom, an electronegative atom. This is, let's say, oxygen, because it is attracting 2 electrons, because oxygen needs 2 electrons to achieve the octet rule configuration. So oxygen is kind of, grabbing the electrons, pulling the electrons towards it. Here, jokingly, this image showing that, it is using the magnet to attract those electrons. Magnetic pole. It's almost like magnetic pole, right? Positively charged nucleus attract additional electrons because the atom becomes more stable if it attracts more electrons. So electrons are being attracted by electronegative atom. And different elements are created equally. So oxygen and fluorine, if you compare, because oxygen is larger and fluorine is smaller, fluorine has higher electronegativity. Okay, let's look at another set. Nitrogen and oxygen. Because oxygen is smaller than nitrogen, oxygen will have higher electronegativity than nitrogen. So I have another joke for you here. So if oxygen and nitrogen are competing for same electrons, oxygen has the edge because oxygen has the higher ability to attract electrons towards itself, because oxygen element is smaller in radius. So nucleus has higher control over valence electrons and can create stronger attractions for the new electrons that are joining the valence electron shell. So oxygen is snatching these electrons compared to nitrogen. And nitrogen seems like taking it gracefully because it says, no problem, oxygen, may the best man win. That's how it works in science. May the best man win. All right. I hope you enjoy these jokes. Now let's move on to science again. So that's the definition, right? We just discussed about it, how we draw. I have one more GIF image here. It's helpful to create as many, useful images as possible. You're saying, electronegativity is the ability of an atom in a compound to draw electrons itself. Let's look at these elements, sodium and calcium. So if you see here, just before they write this plus and minus, this electron of sodium attracted by the chlorine element. So see, this electron is being snatched by chlorine. So we can here confidently say that it happened because chlorine is more electronegative than sodium, right? That's why chlorine is able to snatch it. Do we have any proof to say that sodium is more electronegative than chlorine? Let's see if we have any proof. Chlorine is here, and in the same period 3, you have sodium on the other spectrum and a chlorine on the right side spectrum. So sodium is larger in atomic radius, 186 picometers compared to chlorine only 99 picometers. So chlorine is smaller in size, so it can attract the valence electrons so easily, or it can tightly bind to its valence electron so easily. Why it is useful to tightly bind is there's a greater attractions between nucleus and valence electrons, results in a stronger element, stable element, because electrons love it when it can experience stronger electrostatic attractions from its nucleus. That's why chlorine is able to snatch electron from sodium, because chlorine has higher electronegativity compared to sodium. And in general, metals has least amount of electronegativity because they kind of tend to lose electrons easily because they have a least interest in attracting electrons, because their aim is to reach noble gas configuration by losing electrons. That's why they have low electronegative value. And the goal of these non-metals to achieve noble gas electron configuration is by having an extra electron with them. That's why non-metals have a higher electronegative value compared to metals. I'm going to show you the actual trends now. So here is the table that you have to refer a lot. And these are the electronegativity values of each element, or at least most of the elements in the periodic table that matters. And the most values that matters are between non-metals, the elements that are in blue, and hydrogen. because again here we are discussing about covalent molecules, and covalent molecules are formed by non-metals, and the non-metals are these elements that are in blue. So you only have to mainly worry about them. And sometimes we discuss about group 1 and group 2 metals, but you quickly understand that you don't have to focus much there. So we are going to focus a lot on these elements. See, fluorine has the highest electronegativity value 4 compared to oxygen, compared to nitrogen, compared to carbon, boron. So it is decreasing slowly, right? And also from top to bottom in the same group, fluorine to chlorine to bromine to iodine to astatine. See, it is decreasing slowly. This again because the atomic radius of astatine is much more larger than fluorine. That's why it is decreasing. So you can read it in any way. You can, most famously say that it increases towards fluorine from left to right, and also it increases towards fluorine from bottom to top. So kind of like this, goes like this, from left to right and bottom to top. It increases because keep fluorine as your target point, because chlorine has the highest electronegativity of all the elements in the periodic table. So now again, I want you to make the logical connection between the atomic radius and the electronegativity, because if you build up like that, it makes more sense and it sticks with you. Instead of just learning plainly what is an electronegativity is. That's why I want to make these connections from previous topics to the current topics. Okay, so here are some trends in electronegativity. As we discussed, electronegativity varies with the atomic number because atomic number results in different atomic sizes. Here you can see that as the atomic number is increasing, the electronegativity value is increasing, because as you increase the number of protons in the same period from left to right across the periodic table, the atomic radius decreases. And why it decreases, if you wonder or if you forgot, it is because the effective nuclear charge increases. That's what we discussed in chapter 4, effective nuclear charge. Across the periodic table, the Z effective that we calculated increases. What it means is the capacity of the nucleus to attract outside electrons is larger as you increase the number of protons in the same period. So as the effective nuclear charge increases, atomic radius shrinks from left to right in a periodic table. As the atomic radius shrinks, valence electrons are much more closer to the nucleus in a smaller atom. Because it is closer, the powerful nucleus in a smaller radius atom would like to accept more electrons, because that's what makes it mimicking noble gas electronic configuration. So everything is connected. Now that's how chemistry works. All these basic things are connected. And once you start making connections, you will start enjoying chemistry too, like me. So look at other period from sodium to chlorine. So even in this period across, as the number of protons increasing, because C effective is increasing and atomic radius is decreasing, electronegative values are increasing. Electronegativity values are increasing. From potassium to bromine and rubidium to iodine, similar trend. Some little bit changes here and there. There would be some specific reason. We don't really have to dig into that at this stage. We don't actually focus on that much. Maybe a guy that is doing, let's say, master's or PhD or taking a final year chemistry class might have to know about it in detail. But for now, you don't really have to worry about it. You just need to know that from left to right, electronegativity value increases in period, and from top to bottom, electronegativity values are decreases in groups. That's all you need to know. Okay. So now that we know what is an electronegativity values are, now we are going to use them to define the bonding. Our goal in this chapter is to learn about chemical bonding. We are saying it is basic concepts that we are going to learn in this chapter and apply our applications in next chapter, right? So electronegativity of, non-metals has different electronegative values, as you see in the previous slides, couple of slides. So when these non-metals make bond by sharing electrons, depending on the range of difference in the electronegative values, type of bond is going to be defined. Okay, let me repeat that again. I didn't think it came out nice as I want to say it. So when atoms make bond, okay, so the bond the atoms makes is defined by the differences of the electronegativity of these individual atoms that are making bond. So if the both atoms that are making bond has, similar electronegative value, they make a bond called pure covalent bond. Let me repeat that again. When two atoms make bond, and if those two atoms has either similar or closer electronegative value, comparable electronegative value, they make a bond called a pure covalent bond. It is a bond shared by, it is a bond that resulted as a result of two atoms sharing electrons to make a covalent bond. And whenever the electronegative values of these two atoms are very much similar, we call that covalent bond as a pure covalent bond. In other words, you can also call it as a non-polar covalent bond. Two names. In fact, I just want you to start using that word. Instead of saying pure, nothing is wrong, but if you say this word, you would feel much more comfortable when I start using more that word in future. So pure or non-polar covalent bond. In this bond, the electrons that are shared by two atoms are shared equally. Okay, so as a result, the bond is chemically neutral or electronically neutral. Remember what is an electronegativity is? Ability of an atom to attract electrons towards itself, or in informal words, stealing electrons from another atom. So if are in non-polar covalent bonds, no atom does it, predominantly. That's why we call it as non-polar covalent bonds, or they were electronically neutral. So let me pause and explain the significance of it, of this topic, electronegativity. I'm going to spend lots of time on this topic because we are going to revisit electronegativity multiple times in this chapter once, and in chapter 7 again, and in next term, the Chem 222, at least in 2 chapters, we are going to revisit these chapters again, electronegativity and the type of covalent bonds. Once, if you get it now here, the applications of these electronegativity and covalent bonds looks really easy to you in future. Okay, and also these topics are like basic fundamentals for organic chemistry. If any one of you is taking organic chemistry in future, you would want to master this topic now, so that you can focus on much more complex things. Again, they teach those topics, but learn it now, because not everyone is good in explaining in depth. Not taking credit of all, but I know my favorite topic and I know how to explain it. Okay, so master it now. Save these notes, they will be useful for you in future. Okay, so this is non-polar bond because they share electrons equally. So another type of bond is, we have total of 3 different types of bonds when 2 atoms make a bond as a result of difference in electronegativity. So when 2 atoms make bond, and when those 2 atoms electronegativity differences are considerably different. I'm going to tell you what is considerably different. We have numbers to help, but for now, just know that when they were similar, when they were considerably different. So when they were considerably different, we call the bond formed by those atoms as polar covalent bond. Okay, this is the most popular bond in chemistry. Okay, we have non-polar bonds and ionic bonds. They were existed in many materials and they have their uses. But polar covalent bonds are most popular in chemistry, because if you think of anything like that exists in nature, we don't normally think about it. Like, for example, why oxygen that inhale is a gas, but water we drink is a liquid? Did you ever think about that? It is because in oxygen molecule, when oxygen connected, they have similar electronegativity and they were non-polar bonds and they cannot experience some intermolecular forces. So it's a gas molecule. which is useful to us. It is keeping us alive. And if you are alive and if you are trying to hydrate yourself, you need something that you can drink and stay in your body. That is water. Why it is stable until you boil it to 100 degrees Celsius, and why it doesn't freeze easily until it reaches 0 degrees Celsius. Why it has this magical temperature, boiling and melting properties that saves us and keeps us alive on this earth. It is because it is a polar covalent bond. The bond between oxygen and hydrogen results in considerable electronegativity difference that makes them polar covalent bond, and polar covalent bonds experiences some intermolecular forces, which I will discuss in next term. So as a result of those intermolecular forces in polar covalent bonds, it has these physical properties, for example, water, to keep itself as liquid at room temperature, which is saving us by able to help us hydrate ourselves. So these polar covalent bonds results again because the atom that forms the bond, like hydrogen and oxygen, has considerable electronegativity difference. As a result, they do not share electrons equally. So when they do not share electrons equally, they were electronically active, which is really what we need, right? So when they were electronically active, they attract towards each other molecule, or they participate in chemical reactions. If you think about any chemical reactions that is happening, almost all the chemical reactions, they were happening because there is a polarity in the bond. Unless there is a polarity, you cannot make new reactions. You cannot form new compounds. If you're synthesizing anything, you need to start with a polar covalent bond. It is really hard. There are few exceptions for different reasons, but you need to have a polar bond to start a chemical reaction, to make something. So that polar covalent bond exists because the two atoms that are making bond having differences in electronegativity that is considerable. We are going to go into details what is considerable, what is similar soon in a couple of slides. But for now, general description. So we discussed about so far non-polar covalent bond and a polar covalent bond. The last one is the easiest one, ionic bonds. We already discussed that in the previous chapter. Ionic bonds results because the two atoms that are forming ionic bonds has the large or major differences in its electronegativity. Major differences in its electronegativity. As a result, instead of sharing electrons, they give away the electrons. Remember in the previous slide, I showed you GIF image between sodium and chlorine, where the chlorine snatched the electron from sodium, because the differences between sodium and chlorine is large enough that chlorine can do that to sodium, the metal. So it happens when you have a metal and non-metal trying to make a bond, because they were on the opposite sides of the periodic table. So the differences is really large. Because it is really large, the non-metals will take the electrons away from the metals. It's kind of win-win for both metal and non-metal to achieve the noble gas electronic configuration. So no complaints there from ionic bond sides. But these are the three types of bonds that exist in nature when atoms forms molecules. These are the only three types. One is non-polar covalent bond, one is polar covalent bond, and one is ionic bond. Okay. Now that we know what effect electronegativity has on the molecules and on the bonds, we are going to dig deep into the same topic. And specifically, we are going to focus on both the polar covalent and polar covalent. Okay. And we are going to specifically focus entirely on polar covalent, because that's where action is happening. Non-polar covalent bonds are useful in its own way, but because they were electronically neutral, they were not participating in any interactions between them. So because electrons are not moving, no polarity, so not much interesting stuff to discuss there. But in polar covalent bonds, they were electronically active. They were responsible for all the chemical reactions. So a lot more to discuss on polar covalent bonds. So we are going to eventually focus on polar covalent bonds. And if you take again organic chemistry, Polar covalence bonds are everything that you discussed there. Polarity is everything that you need to know. You need to know electronegativity and polarity to be successful in organic chemistry, or if you want to be organic chemist, you need to know those topics really well. Okay. Now let's discuss, what is the effect of this electronegativity in a bond. I'm saying, one bond is nonpolar, one bond is polar, one bond is ionic. How it looks like. So this is how it would look like, and these are the electron density maps that were obtained by taking the X-ray of the molecules. Okay, so we have physical proof that electrons are where they were in these molecules. So according to the X-ray map of the electron density of these molecules of H2, HF, and NAF, you can confirm what we just learned previously, that in a nonpolar covalent molecule like H2, right? H2 is a nonpolar covalent molecule. Why? Because it's the same atom that is connecting with the another same atom, so no chance of having different electronegativity. So there is no difference in electronegativity between two hydrogen atoms. So it is going to form nonpolar covalent bond. And when it forms nonpolar covalent bonds, it's supposed to share electrons equally so that it will be electronically neutral. See, the red cloud is electrons. You see where the red cloud is here? Here is the red cloud. I couldn't find it. Let's see. Let me get a pen. Oh, no. Let me get a different color. Green, purple. Okay, I got a different color pen here. You see, here is where electron density is, right in the center. You have hydrogen and hydrogen on both sides. Here is one hydrogen and here is one hydrogen. They are sharing electrons right in the center, like fairly, because it is a nonpolar covalent bond. And HF, you already see the chart. You can now, if you have the chart with you, which I suggest you having handy all this time while you are listening to this lecture, have that chart next to you, electronegativity chart. Fluorine has electronegativity of 4, hydrogen has electronegativity of 2.1. The electronegativity difference is large enough, considerable. Because it is considerable electronegativity difference, HF bond is a polar covalent bond. It is still a covalent bond because whenever two nonmetals make a bond, it has to be a covalent bond because they share electrons between them instead of giving away electrons. So whenever they share electrons, we call it as a covalent bond. But the question is if that bond is a nonpolar covalent bond or a polar covalent bond. So HF bond is a polar covalent bond. So in polar covalent bonds, as we discussed, electrons are not shared equally. They share electrons, but they were not shared equally. Electron cloud is tilted towards the more electronegative atom because electronegativity is the ability of attracting electrons towards itself. So if you have hydrogen here and a fluorine here, you can clearly see that electron cloud, which should be in the center, is shifted towards the fluorine and staying next to fluorine more. So which makes the HF bond electronically active because hydrogen is kind of lost electrons. It's kind of, its plan is to share electrons with fluorine before it make a bond, and once it makes bond and fluorine is like, oh, I'm more powerful than you because I have stronger electronegativity value, so let me snatch those electrons that we are sharing towards me because I need it. Hydrogen cannot do anything because it has less electronegativity value. So because of that, it creates the polarity in a bond. It makes the bond electronically active, which is a good thing. Don't get me wrong. This is the best thing that happened to us, the humankind, or for the life that we are living. Unless we have this polarity, life cannot develop on its own. Everything that we are creating, or we are living, the living body mechanism, the molecules that we are made up of, everything majorly is from the contribution of polar covalent bond. That's why I love electronegativity values. So let's look at the last example, sodium fluoride. So sodium fluoride is made up of sodium, a metal, and fluorine, a non-metal. So pretty easy to guess. It is an ionic compound. So in an ionic compound, electrons are not shared. They were given by one element, a metal, and taken by fluorine, a non-metal. So here you can clearly see they were just electrostatically attracted to each other, but they were not sharing electrons between them. They're just, stuck together because of electrostatic attractions, but electrons are entirely with sodium. Sorry, entirely with fluorine. Okay, these are the, applications of electronegativity, how differences in electronegativity affects the electron density in a bond. Is it present in the center, like in the first molecule, or is it present more towards one element, or entirely on one element? It's different. So that's why we need to learn this so that we can confidently comment on things like chemical reactions and explain reasoning behind, phenomena that are happening in chemistry. Okay. So this is what I want to make, because by the end of this lecture, or maybe by the end of this chapter or next chapter, you're going to come to me and say like, oh, you say this bond is non-polar, but this is kind of acting like polar now. And you would come to me like, you call this bond as ionic, but it's kind of acting like a polar covalent. Why is that? So it is because you cannot make boundaries between a non-polar to polar to ionic. They were arbitrary boundaries. We can generalize things, but you cannot certainly say like, this is always going to be polar, non-polar. This is always going to be polar bond. This is always going to be ionic bond. There is, arbitrary boundaries. They show mixed characters, but what we just discussed previously is going to be true. And we are going to use the general guidelines, but don't go to your grave with these general guidelines. Be flexible. They work like 99% of the time, and only time they don't work is because those arbitrary boundaries, they just changes minutely. That's where you need to be flexible, like, oh, this is the matter that we are talking about, these are the atoms that we are talking about, they have their own issues. So we cannot, we cannot create boundaries. That's what I'm saying. That's why, be flexible between understanding a bond as a non-polar covalent and a polar covalent and an ionic bond, because they were just arbitrary boundaries. And when I explain the topic towards the end of this lecture called percent ionic character, it makes a lot of sense why I am talking about this underlined topic. Percent ionic character is the topic that you're going to look forward to for me to say that there is no sharp distinction between them. We have a mathematical proof to say that. Okay, so let's go through this, following rules that helps us determine what type of bond we have. So we said we have three types of bond: non-polar covalent, polar covalent, and ionic bond. And when I said that in the previous 2 slides ago, I used the word, similar electronegativity value, considerable differences in electronegativity value, and a major difference in electronegativity value. What are those values are? These are the numbers that you are going to look for. When two atoms make bond, and if you are trying to identify if the bond is what type of bond, first you need to identify the differences in their electronegativity value from the electronegativity chart I showed you. Remember, each element has assigned electronegativity value. It is a chart. It is, fact. It is an identified number. So we take that. We take the difference between them. Simple math. And once you do that, you would come up with the 3 major categories. One is the difference between two atoms' electronegativity is less than 0.5. That's what we call it as, similar electronegativity difference. It's not significant enough to make the atom electronically active. No one is trying to steal electrons from anyone if the difference is less than 0.5. And we call the bonds made by such kind of atoms as non-polar covalent. Okay, what is an example is, we already discussed bond between hydrogen and hydrogen. Let me save lots of time and frustration for you in future. The most popular or major nonpolar bond that you see in chemistry is carbon-hydrogen bond. Carbon has electronegativity of 2.5, and hydrogen has the electronegativity of 2.1. So the difference between them is only 0.4. That's why carbon hydrogen bond is electronically neutral, because it is a non-polar bond. So it is not participating in chemical reactions. It is so hard to make changes to carbon hydrogen bond chemically. Now, in future, we are going to achieve some results. We have to apply some special chemical reagents, but it's not natural for a carbon hydrogen bond to be chemically active. They're kind of inactive. Okay. So next type of bond category is when your electronegativity difference is somewhere between, somewhere between 0.5 and 2. In those cases, you call those bonds made by these atoms that has these considerable electronegativity differences polar covalent bond. Those are what mainly we are going to focus. Example HF, it has at least 2 electronegativity difference. HCl, HBr, or CCl, CF, or NO. All of these bonds has the electronegativity difference that falls in this category of 0.5 to 2. And last category is ionic bond. When ionic bond is observed, when the difference is at least 2 or more, the difference in electronegativity, if it is between 2 or more, then that's the signal indicate that you have an ionic bond. And also it should be pretty easy by the eye test to identify where is an ionic bond is. If you look at a molecule, if it has at least one metal, you have at least one ionic bond there. Because metals cannot form covalent bonds with non-metals. It never happens. So look for a metal for an eye test to identify if you have ionic bond or not. Okay. Now let's move on and apply what we just learned. For some reason that I cannot get rid of. Please don't mind that ink. Oh, you cannot see the ink on this slide, but on this slide. Okay, it's not your issue now. I have some issue going on here. So let's look at the question. Classify the following bonds as non-polar, polar, or ionic. Okay, so what are those? CLF and CsBr and C2H4. Okay, let's work on CLF first. What do you have to do whenever you are asked to identify type of bonds is first you need to have the electronegativity chart with you, because without the chart you don't know their electronegativity differences. And if you remember, most of them it is great, but it is not a common expectation for you to remember. Again, if you remember, it is great. If you study long enough, if you study chemistry long enough, you would remember, you would identify trends. But initially, at least use the chart. So identify difference between chlorine and fluorine electronegativity values and see where it falls. And identify electronegativity difference between Cs and Br and see where it falls. And identify difference between C2H4, the atom between C and H, because you don't have to check the electronegativity difference between 2 of the same atoms, carbon and carbon. Okay, that's what you have to do. So these are the electronegativity values of all the elements that are present in these molecules. And first one, your answer should be that it has to be a polar covalent bond, because the difference in electronegativity between CLF, chlorine and fluorine is 1. Is 1. So it is a polar covalent bond. And in CsBr, your eye test should tell you that it is an ionic bond, because cesium is a metal. You don't really have to show it unless I ask you to show you the work. Here the difference in electronegativity is 2.1. Right? Next molecule, C2H4. In C2H4, you have the heteroatom bond is carbon and hydrogen. I already showed you in previous slide. CH bond is non-polar because it has the electronegativity difference of only 0.4. So you don't. So your answer for C2H4 is it is a non-polar covalent bonds. Okay, that is how you would identify a type of bond present in a molecule. Okay, so what we discussed so far, we started with my favorite topic in chemistry, discussing about electronegativity of an atom. And I spent large amount of time on explaining why it is so important. I know I'm spending lots of time on this topic because trust me, it is going to save you lots of time and frustration in future if you completely get it now. That's why I'm going slowly, thoroughly, making sure you get it. Electronegativity is able to have an atom to attract electrons. So different atoms has different ability. Because of that ability in a bond, some atoms trying to attract electrons towards them, which creates polarity in a molecule or no polarity in a molecule, or ions between atoms. So as a result, we defined the type of bonds as non-polar covalent, polar covalent, and ionic bond. Okay, and I said no action is happening on non-polar covalent bonds, and you don't really have much to discuss on ionic compounds also because they were just ions and they were so visible what kind of ions they were. So only discussion that happened to be happen is on polar covalent bonds because that's where all the action is happening, because polar covalent bonds are the ones that are responsible for almost all the chemical reactions that are happening because the difference in electronegativity values in a bond. So because of that, we need to learn more about polar covalent bonds. That's what we are going to do now, trying to learn more about polar covalent bond. So when you try to learn about the polarity in a molecule, these are the things that comes to mind. You need to learn about dipole moment, an indicator of how polar a bond is, okay? And partial charges, again, another indicator of how polar the bond is. And a percent ionic character of a polar covalent bond, again, an indicator of how polar the bond is. Now, polar covalent, again, if you guys remember the attention information, I said there is no special distinction between polar covalent bond and ionic and non-polar and polar. It's just, arbitrary. So polar covalent bonds might as well act like ionic so that you would identify based on a percent how much it is acting like an ionic bond. There must be some percent, like 5%, 10%, 20%, 50%, like that. So these are the three things that define polar covalent bond. If you get all these three, congratulations, you are kind of, in higher level of, knowledge in chemistry that, help you understand like a lot more complex information, a lot more complex concepts with much ease if you get the hang of these three topics: dipole moment, partial charges, percent ionic character. Again, these three topics are entirely related to each other, and they were focusing on polar covalent bond. As you see here, I have a polar covalent bond HF. And how do we know it is polar covalent bond? It is one molecule, right? There are no two single atoms as hydrogen and fluorine. You see one molecule HF, but the electrons are here on the fluorine side. That is how we know that it is a polar covalent bond. So blue regions where electrons are not really coming over here are coming over very less time, and red region is where electrons are staying mostly. Now, we just show like that, electrons just revolve around fastly, but the number of times electrons goes to hydrogen is a lot less compared to number of times electrons stays near fluorine. That's why red is mostly towards fluorine here. Now, as we discussed, red region is where the electrons spend most time. Now that we already know that, wherever the most electronegative atom is, electron goes towards them, we are just going to use the signs to show them, okay? Those signs are, there are two different signs. One is using a crossed arrow like this. See, an arrow across with a cross at the end. That is a symbol to show that bond is polar and it has the dipole moment towards the fluorine. You only use that arrow on polar covalent bonds, and you use it to show where the dipole moment is going towards. Dipole moment is basically where the electrons are staying, at in a bond. So showing towards fluorine is indicating that dipole moment is towards fluorine, okay? And another way of showing that bond is polar is using the partial charges. Now remember, covalent bonds are not ionic bonds. You don't have ions. You just have atoms, but they pull electrons towards each other if they have difference in electronegativity values. So because hydrogen and fluorine has larger difference in electronegativity value, they pull the electrons towards one side compared to another, and we are using these partial positive and partial negative symbols to show that negative charge means electrons. So we are using negatively charged symbol. We read in chemistry as that symbol that you see here. This one we read in chemistry as partial. You write like delta, and we read it as partial. That's what I'm going to call it as partial negative charge towards fluorine, fairly, because fluorine is more electronegative. And this one we call it as partial positive charge because it is least electronegative of both the atoms, and it loses electrons to fluorine in a bond. So partial positive and partial negative. So this is partial charges topic. And this one is dipole moment. And in next couple slides, I'm going to show you how to calculate dipole moment, how to calculate partial charges, and how to calculate percent ionic character. That helps you get the full picture of a polar covalent bond, hopefully. All right. So let's go over the dipole moment now. Okay, that's our first assignment. Talk about dipole moment. Dipole moment is the quantitative measure of the polarity of a bond. Now, same polar covalent bond, right? But I don't have any metric to see how much polar it is. So that metric to comment on how much polar the bond is, we are going to use a dipole moment, because that is our metric to say, is it highly polar or mildly polar? There can be different polar bonds. So depending on the number of dipole moment, when you see that number, you can comment if it is highly polar bond or not polar bond. And this is how you would calculate. It's a simple formula. This is nu. We call it as nu, and it is a symbol that we use for dipole moment. And a Q is the partial charges. So how do you get the dipole moment is multiplying the partial charges with the R, the distance between atoms. Okay, it's a simple formula, right? So again, Q is the partial charges on the atoms. In the previous slide, I showed you partial charges on hydrogen and fluorine. That's the Q is. And R is the distance between them. And you just need to know what units they are going to follow. Nu, the dipole moment, is expressed in Debye units. And to calculate the dipole moment in Debye units, you need a conversion factor for the charges and distance, because Q, the partial charges, is calculated in the coulombs. Charge is calculated in coulombs, and R, the distance between atoms, is calculated in meters. So if you're expressing the dipole moment in Debye units, you need some conversion factor. So this is the conversion factor between Debye and coulombs and meters. We are going to use that. All right, let's use our energy. Well, before I move on, I guess I just want to remind you the values again of the dipole moment. I just have a general, couple examples to show you the dipole moment differences. So here is the electronegativity chart. Again, I'm going to use that chart a lot, and I'm going to show you the chart multiple times. So dipole moment, let's see how it is related to type of polar covalent bond. Look at this table that you are looking here. So here you have a comparable bonds. Same group elements is making bonds with hydrogen. So from here, fluorine to chlorine to bromine to iodine, okay, from top to bottom. What do we know about these four is chlorine has higher electronegative value compared to chlorine, bromine, and iodine. Okay, so now we know that hydrogen has fixed electronegativity 2.1. So if you try to identify differences in electronegativity between HF, it is going to be larger compared to HCl difference and HBr difference and HI difference, right? So which means HF bond has to be mostly our largest polar bond compared to HCl, HBr, and HI, and HA has to be least polar bond. Let's see if it is indicated by dipole moment correctly. So I'm calling HF is the most polar bond, and here I'm seeing the dipole moment of 1.82. Let me get another color. And I'm calling HF as the least polar bond, and I'm seeing dipole moment of 0.44. Seems like it is following the trend, the dipole moment, because dipole moment is an indicator of the polarity of a bond. Higher the polar, higher the dipole moment. Lower polar bond, lower the dipole moment. That's why you are seeing this trend. If it is going down because the electronegativity differences is decreasing between these two atoms that are making bond, so does the polarity of the bond, and so does the dipole moment. And what we are going to do is we are going to use this knowledge and trying to apply to understand, if we understand this topic, right? So what the problem that we have here is our ultimate goal is to determine the magnitude of partial positive and partial negative charges in the HF molecule. That's our ultimate goal, but let me spend a couple of seconds explaining the reasoning behind why we are discussing. So HF, the hydrofluoric acid, is dangerous like any other acid, very dangerous, especially if it is, well, not especially, it is dangerous. So don't even try to get in contact with it. So because of that, if at all you get exposed to it, it can burn the skin, it can destroy the skin because it is very powerful polar bond. So as a result of that, we should be very cautious if at all you are going to be used HF. But however, it is asking us to calculate the magnitude of partial positive and partial negative charges in HF. How do we do that, right? Is it possible to calculate the partial charges in HF? If you guys remember, the only thing that we know so far, anything about partial charges, is the dipole moment mu is related to the Q, the partial charges, and R. That's the only equation that you knew. Okay, so is it anyway possible that we already know the dipole moment value? In fact, we do. In the last slide, I showed you that HF has the dipole moment of 1.82 Debyes. And is it possible to get the distance between hydrogen and fluorine? It has to be a tabulated value, and you will get shade that value. So once you have both of those values, you could use the dipole moment value and the distance between atoms, and you can try to identify the partial charges that are present on hydrogen and fluorine. Okay, let's work on that. So here are the values that we are going to use: the dipole moment and the distance between atoms. So using these two, we are going to identify the partial charges on hydrogen and fluorine. The units that we are going to end up with for the partial charges is coulombs. Charges are expressed in coulombs, electronic charge or proton charge or any charge, you should express it in coulombs, excuse me. So R, the distance, is available currently in Angstroms here, but you need to convert that into meters because dipole moment dBi can be converted into coulombs and meters. So that is how you can cancel the meters. Okay, let's focus on dipole moment value now. Dipole moment is 1.82 dBis. dBi is not in coulombs and meters yet, so we are going to use the conversion factor. 1 dBi is equal to 3.36 times 10 to the power of -30 coulombs and meters, so that we can cancel the dBis, the unit, and end up with the dipole moment in coulombs times meters, which is what necessary for us to get the final answer in coulombs. Now we have the radius in 0.92 Angstroms. Angstrom is not meters, so you need to use the conversion factor between Angstroms and meters. 1 Angstrom is equal to 1 times 10 to the power of -10 meters. Now we are going to cancel the Angstroms like this to end up with, radius, atomic radius between hydrogen and fluorine as 9.2 times 10 to the power of -11. Okay, now that we done that, we are going to use these two values to identify the charge, the charge Q in the Coulombs. So Q is going to be U over R, the dipole moment U over R. We already identified U before in the previous slide and R, so we arranged one over another to cancel the units meters, and we end up with the charge of the Coulomb, of the charge in Coulombs, like we are supposed to. Now, the question asks you to express the Q in partial charges, okay, partial electronic charges. How do we do that is, we are going to use the relationship between charge of one electron with the charge in coulombs. There is a relationship, a standard relationship. One electron charge is equal to 1.602 times 10 to the power of -9 coulombs. So using that as a conversion factor, we are canceling the coulombs, the unit, and ending up with the partial charge of 0.41 electrons. That is the partial charge that we come up to be. So what is that 0.41 electron is saying us is that hydrogen polar bond leave the partial positive charge of 0.41 on hydrogen and a partial negative charge of 0.41 on fluorine. Then remember, HF bond is a covalent bond because they share the electrons between them. But because the fluorine is electronegative, because fluorine has a greater electronegativity value than hydrogen, it attracted more electrons towards it. And we were able to amazingly count how much of that extra 1 electron it is able to steal from hydrogen. Out of 1 electron that hydrogen shared, fluorine is able to gain 0.41% of it. So what hydrogen lost is 0.41% of its 1 whole electron. What it showed us is that there is a polar covalent bond, and you can clearly calculate how it is working. All right. All right. Let's see what we are going to discuss now. Yeah, we are going to focus on our last topic, percent ionic character. How do we calculate that? Okay, because if you remember, this is what we discussed previously. There is no clear distinction between them, but they were just arbitrary boundaries. We are going to discuss why it is that, why I'm making that comment that they were just arbitrary boundaries. Now, we still majorly categorize them as nonpolar, polar, covalent, and ionic, but if you go into specific details, like you don't have to in general chemistry class, but in future, maybe if one of you decide to do PhD in physical chemistry, this is what you do. You're going to be very picky, and you wish to describe bonds as percent of ionic character it has instead of saying it is polar or non-polar, because that's what you do if you're going to do PhD in a specific topic. So how do you do that is by using this formula. You use the percent ionic character formula to identify how much of percent ionic character a bond exhibits by using the dipole moment observed over the dipole moment assuming the standard charges. I'm going to show you how this formula works. Pretty fun to work with, this formula is. Let's see, what are the results? Let me just show you the trends of that formula. Right, these are the trends of that, calculating percent ionic formula. If you see here, the bonds at the bottom, IBR is present at the bottom. What is an IBR? A bond between iodine and bromine. They have like 0.3 electronegativity difference. It is a non-polar covalent bond, so its ionic character is close to 0, like really close to 0. Let's see, ICl. ICl is a bond between iodine and chlorine. It has the electronegativity difference of 0.7. So it is mildly polar covalent bond because it just crossed 0.5. So here, if you see the polar covalent bond, it has some ionic character in it. As you see here, HBr has a little bit more ionic character compared to HCl. What it tells us is, and let's track HF as well. HF, the most polar covalent bond of all, has the almost 40% ionic character. What it means is, in the previous slide, what we just able to identify is fluorine and iodine has 0.41 extra electron cloud. Fluorine has 0.41 extra electron cloud compared to hydrogen. That's why it is able to show up at the 40% of ionic character. Ionic character is, ions presence. So in polar covalent bonds, you don't have ions, but you have partial ions, partial charges that you can represent in terms of percent ionic character. Because fluorine has 0.41 electron cloud, it has about 40% of ionic character. That's how you would read. So let's look from top to bottom. So here the bonds formed by lithium fluoride. Again, you can see it is mostly ionic bond because the difference in electronegativity is almost 3. Even then, it's not completely 100% ionic. As a matter of fact, all of these bonds that are made by a non-metal and a metal, they were not 100% ionic. What it's saying is they were still trying to share the electrons between them, even though they were ions. So they were ions, they have ionic character, but they were mildly showing covalent character. So how do we know? Because it doesn't have 100% ionic character. All of these elements, they have less than 100% ionic character. What is the rest of it made by is covalent character. So let's look into how to identify, how to calculate ionic character using the next problem here. Okay, let's look into this problem. The problem is asking us to, using the data from table 6.2, calculate the percent ionic character of the bond in HF. Okay, bond in HF. An HF bond is made by hydrogen and fluorine, and it has the electronegativity difference of, let's see what, iodine has electronegativity of 2.5 and hydrogen has the electronegativity of 2.1. So the difference in electronegativity between them is only what, 2.5 and 2.1, 0.4 less, right? Not much. So it is a non-polar covalent bond. So for a non-polar covalent bond, it is asking us to calculate the percent ionic character to see if it has any ionic character. So what we have to do for that is we are going to calculate the dipole moment using the data that we have, like the distance between them and the charges between them. Well, actually, we don't have to do that because say table 6.2 thankfully already gave the dipole moment between hydrogen and fluorine, which is 0.44. So you don't have to do that. So what you have to do is you have to calculate the dipole moment for, like, assuming when both hydrogen and iodine are acting like ions, because we got data when hydrogen and iodine are acting like non-polar covalent bond. When hydrogen and iodine are acting like a non-polar covalent bond, the difference between polarity or dipole moment between them is only 0.44, non-polar covalent bond. But when they were acting like ionic bond, assuming that they were acting like ionic bond, because we are trying to identify ionic character, they both should have full 1 electron. Iodine should have full 1 extra electron, and hydrogen should lose full electron it has. That's what ionic bond is. Because of that, we need to identify what is the assuming dipole moment when HF is acting like a ion. When HF is acting like this, it doesn't because it's a non-polar covalent bond. But just for the sake of calculating ionic character, we need this value. When iodine is -1 and hydrogen is +1, that is when it is like, presumable hypothetical ionic character. So for that, you need the partial charges and the distance between them. Here we are trying to identify dipole moment for H plus and I minus 1. It's like ionic HF. It is weird, but we have to calculate it, right? So the charges in coulombs is, what is the charge of an electron is? Q, the charge of an electron is it is already defined value. It is a fixed value. The one electron charge in coulombs is 1.6022 times 10 to the power of -19 coulombs. It is a fixed value. So we are going to use it right away. And the distance between them is, let's say, 1 Armstrong. When you convert to meters, this is how you get, or maybe it is 1.61, sorry, 1.61 Armstrongs. When you convert to meters, this is what you get. And when you convert to when you solve the Q times R, you get 2.58 times 10 to the power of -29 coulombs and meters, but your dipole moment should be in dBi. So we are going to use the dBi conversion factor to convert the 2.58 times 10 to the power of -29 to 7.73 dBis. 7.73 dBi is the dipole moment if hydrogen and iodine are in ionic bond. I know it is not, but just for the sake of calculating percent ionic character, we are assuming it. Okay, so then let's calculate the percent character, because we know what is the actual dipole moment of HF when it is a non-polar bond, and now we know the dipole moment when it is a ionic bond, hypothetically. And using these two, we are going to identify percent of ionic character just by taking actual over hypothetical, assuming it is an ionic bond. And it happened to be that HF has only 5.7% of ionic character. At some point in this term, I'm going to ask you to calculate ionic character of a molecule, and you need to know this. So please review it again if you don't get it, or we can rediscuss the topic again. It is what you have to do. You only have to calculate the ionic character of a molecule if it is hypothetically going to form ion. So that's how we calculated here for HF, hypothetically if it has +1 charge, and how much it is going to have the dipole moment. Very simple calculation, and you are taking that over the actual dipole moment, which will be given to you. You don't have to calculate this, and you can calculate the percent ionic character like that. So this is the end of this topic. I just want you to, remind you again. That's why we don't have a specific boundary lines between, non-polar and polar and ionic. There is always a chance of percent ionic character. Actually, percent ionic character is the one that is correctly describes the nature of a bond, but you don't actually need it all the time. You only need it if you are so picky. And I'm discussing this so that you can be flexible, not picky. Okay, in general chemistry class, you can just need to be flexible. But in future, if you are going to be a chemist, you can be picky by calculating percent ionic character for every bond that you come across and be a nerd. Okay, thankfully I'm not one of those. Yeah, that's all I have. I know it is 1 hour 15 minutes, but I hope it is totally worth it. Please don't hate me. I really love this topic, but that's maybe a partial reason to talk longer, but this topic kind of needed. I could have maybe explain all of this in 15-20 minutes, but I would lose half the class if I do that. Only I will be the guy that has the complete knowledge over electronegativity instead of all of us having the knowledge on electronegativity. That's why I took my time and I explained slowly, went over multiple times, reviewed it so that we don't have to worry about it, because every minute that you spend here, you're not spending in future when we review these topics, when we talk about the similar topics. You will have such a great command if you just nail this topic over right now, which I want you to do. Okay, I'm going to see you in another topic. Take rest after this lecture.